talk about profunctors. Profunctors, like so many topics in category theory, can be approached from several different angles. John Baez talks about how there's kind of this landscape in category theory about concepts just being linked together in many different ways. And sometimes it's very hard when teaching this stuff to know which way of approaching it is best, particularly when students are coming from different backgrounds, where certain ways of approaching it will resonate with them more than others, and you have a diversity of different needs for that. Profunctors at a practical level in programming, in Cat Colab, in categorical modeling, play a really interesting role. And you'll find them in the pages of David Spivak and Brendan Fong's 7 Sketches, particularly with V profunctors and enriched categories for reasoning about like optimal cost or optimal minimizing distance or building things with greatest efficient use of resources, etc. And it's a powerful presentation there. But profunctors are linked to a lot of other topics, and I actually have something like 6 lectures on profunctors that I've come up with over the years. But like so many topics in category theory, they may seem really mysterious until you have a certain Satori moment, a certain epiphany, and you realize, oh, it's just that? Like, okay. Like a lot of these things, once you get your grip on some basics and you have a couple examples in mind, John Baez talks about having like 5 or 6 examples of concepts being really valuable for thinking about them and making sure you understand them well. Then you can do very well. And fortunately, profunctors is an area where there's some wonderful intuitions. And I'll be talking about those intuitions today before we get into some of the more nitty-gritty notation and kind of reasoning about them. The truth is, you've all seen profunctors before in a certain way. There's a HOM profunctor that we use quite a lot in describing a category when we talk about like the set of arrows, set of morphisms, a plain old category, not double category here, from object A to object B. We write it as, C, the category name, and in parentheses A comma B, right? And that's actually a HOM profunctor there. And we just always apply it routinely to objects, but it can be applied to morphisms, and that's where so many things in category theory the real magic comes in. So I want to talk about some intuitions with profunctors, and in my discussion of them, I will try to come at it from different angles. A programming angle, as well as an angle associated with double categories and double theories, as well as an angle associated with some modeling, etc. Okay, so one way I like to think about profunctors that's very common, very prevalent, is as bridges. Okay, so So a profunctor uh, can be thought of as like a bridge. Bartosz Milewski talks about it as like a proof relevant relation, a way of relating things that has particular paths associated with it. You can think of it as associated with ways of getting from like an object A to an object B. Uh, um, Ways of turning an object into a B or making a B from an A. Um, and and it operates on morphisms. It's a functor. Functors, their jobs in life. It's related to a functor. So like a functor, it can operate on objects, map objects to objects for a traditional functor. But it can also operate on morphisms, right? A traditional functor maps morphisms in the source category to morphism in the target category. It's a structure preserving mapping. And profunctors have that feeling as well. You can apply them to objects, and you can apply them to morphisms. But they're going to take two pieces of information, not just one. A functor, we might think of it as like, if we're dealing with Hask, right? We might think of list of A. A might be an object representing a type, right? It's an object in Hask category, pseudo category Hask. And list of A maps that object to another object, another type. List of A, right? It's a type. But with a functor, we can map morphisms as well, right? We can map. So if we have a type int and another type bool, and we have a map from ints to bools, with a functor, we can do fmap. We can lift that morphism, that function from ints to bools. So it goes from lists of ints to lists of bools, right? So functors map objects to objects, morphisms to morphisms in ways that honor identity and honor the identity morphisms on objects and honor composition, right? They preserve composition. A profunctor can be thought of as like a generalization of a functor, okay? So we might write a functor from C to D, but a profunctor from C to D, we can write a profunctor as something that goes from C to D. But we often do it with this little slash in the middle of the map. So I'm going to say this is a profunctor, okay? And like a functor, it's going to lift objects here to objects here, and morphisms here to morphisms here. We could kind of think of it like that, but it's a generalization. One of my earliest encounters with profunctors was when someone asked David Spivak, could a functor map an object of C to no object of D? Could it map an object of C to many objects of D? Kind of like a relation between C and D. And David Spivak said, oh, for those things, you need a profunctor. And indeed, it's like a generalization of a functor that allows you this greater flexibility. It's more like a relation, which is why profunctors are associated in a double category theoretic context with pro-arrows, which are used for relations as well. We'll come to that. In fact, they give the name to pro-arrows, profunctors. And we can think of a profunctor from C to D as it's very fruitful, very handy, very powerful to have this in mind as a map from, I have C to C here, but this could be two different categories as kind of showing a bridge from C to D, okay? I wish I had it with two different categories here shown. I'll have to I'll have to come up with that in a different one, but maybe I'll just see like Profunctors 2. Do I have a nice map of between two different categories? Oh, this is on different stuff, applications of Profunctors. Yeah, these are all the same basic one. Okay, so this is a profunctor where it happens to go from C to C, but you can imagine this being one category and this being another. And the profunctor is going to be able to map an object here in C to 0 or more objects over here. And a morphism here to a morphism over in so I think it's fair to say 0 or more morphisms in D. I'd have to think about that. But what's even kind of a nicer notion here is that we think of the profunctor as having bridges. So all these thicker, brighter lines are the bridges associated with the profunctor. So here are all the morphisms in C. They're shown here in these, straight as an arrow type of lines. Here are all the morphisms in the target category. But the profunctor provides these kind of bridges between these. Imagine these as like different cities, right? Or in this case, same city. But there's like bridges from this object over to this, or this object to this. Maybe it's Saskatoon on both sides, and there's bridges from one place in Saskatoon, the university area, to the area of the Parktown Hotel on Spadina. Or there's one from Broadway area to 21st Street near the Radisson Hotel there, right? This bridge is what's provided by the profunctor. Okay, it provides these bridges, and we call these heteromorphisms. These bridges, they're heteromorphisms. They're not a morphism in C. They're not a morphism in D. They're a connectivity between these. Okay, and so this is called a collage for a profunctor. In this case, a profunctor from C to C. And you'll notice an object can go to 0 or more of these. And you'll notice that that can lead to a much different mapping than you might expect. In some categories, but some functors rather. Where you have, one going to a particular one over here. Now, what's really important when we think about a profunctor acting on morphisms is that a profunctor allows, let's take this mapping of C over here to C over here. Happens to get a C. Wish I had a better example, but to C here. Okay. Yeah, maybe I'll do it with this one, this green one. B maps to C. So the profunctor maps B to, among other things, C here. Okay. The profunctor is actually going to map B and C to a set of bridges. That's what, and one of these bridges is this one, G. This one goes up like that from B to C. A profunctor is going to allow pre-composition in C, like you can extend it backwards in C, like, and you can extend it forward in D. So in this target category, you can extend it forward. The profunctor is going to support this ability to kind of have pre-composition in C and post-composition in the target category, and thereby connect things, right? The fact that we have this bridge from B to C means we have now a way of going from A to C, right? We can go from A to B and then B to C, right? But this bridge that is provided from B to C also means we have a way of going from B here to D, right? Because we can go B to C and then C to D. Through this heteromorphism G, we can go, extend post-composition, as we say. Go down here with that, right? And more than that, right? We actually have a way from going from A to D, right? We can go A to B, B to C via the Profunctors connection, right? And then C to D, right? And so there are these induced maps, and I've actually drawn it here as a dotted line, right? Going with F and then G, that's the green one here, and defined by the profunctor, and then H. The composition of those arrows lets you go from A to D, right? And what I want to draw your attention to here for your intuition is that the profunctor, by bridging these two categories, it has this asymmetry of sorts, right? And for the source category, it's about pre-composition. It's about ways of getting from objects here, biomorphisms, to the bridge, right? But for the target category, it's about post-composition, ways of getting from that terminus of the bridge here, C, to later objects to objects in D that are downstream of it. So for the source, it's kind of upstream things that we can get to. For the target, downstream things that we can get to. And we're going to see that this pre-composition in the source, post-composition in the target, is very closely related to how it lifts morphisms. It's how this profunctor operates on morphisms. Because it not only maps objects to objects, but it maps morphisms to morphisms. And how it does that is through pre-composition on the source side and post-composition on the target side. So it's very useful when we're talking about profunctors to keep this idea in mind of a bridge. There'll be lots of notation that maybe will obscure it in your mind, but just keep on coming back to this notion of a bridge. And among those things, a profunctor handles lifting via pre-composition in the source, post-composition of the target. And for any pair of objects, the profunctor gives a set of heteromorphism, bridges that go between those two objects, the one object in the source, one object in the C, in the target. So it's kind of like a translation mechanism, a way of kind of translating from C over to D, but also kind of linking up, right? C and D in a very natural way. So that was showing a profunct from C to C, but in general, we have one from C to D, and the general picture holds there. You've seen how it can be like a little bit of a generalization of a functor, maps particular objects to more than one object, and or to no objects. But this, what I showed you in the picture, can be expressed symbolically as talking about a traditional functor from a product category, the category of products, morphisms and objects, from C op cross D, where op is right the flip side of this, C, all the morphisms are flipped around, cross D. set. So let's unpack that. I'm gonna maybe I'll take this here thing, and I'll go back to that picture on Profunctors. Okay. So here we go. So I told you a profunctor there, sort of considered as a mathematical object, is a functor from C up cross D to set. Now let's try to get some intuition for that, because it may seem like really wacko type of thing. Like, why do you have this op here? Well, the op here is related to it having pre-composition back here versus post-composition at D. C is kind of op compared to D, and that's why we're dealing with pre-composition, post-composition. But let's consider what's going on if we take, well, this is a functor. It's a functor, okay? So I'm saying it's a functor from this. And imagine the right one is D, not just C, it's D. Okay. So if it's a functor, it maps objects to objects. Well, what's an object in this? Can anyone tell me, if we have a product category, what's an object in a product category? Anyone say? Well, it's a product of objects of each of these pieces. What are the objects of C-op? So if we consider the category C, we know it's objects and morphisms. What are the objects of C-op? What are the objects of C-op? We know the morphisms are flipped around. What are the objects of C-op?
Same as the objects of C.
Same as the objects of C. So the objects of C-op are objects of C, plain old op. And the objects of D are the objects of D. So an object of this product category is just a product of an object of C and an object of D. Okay, so it's a pair, like B and C. And
sorry,
yes,
it's the same object, but the different direction in the morphism. Just
it's the same. So C-op
object. It's the same objects, but different. My means is reverse.
Reverse. The morphisms
yeah,
reverse.
the morphism.
That's right. That's exactly right. So C-op has the same objects as C. The morphisms. So I'm going to say it the way Eugenia Chang said it. So I know I'm on good ground here, but it's going to take your head maybe a bit of time. Everyone's had a bit of time to get over. So the objects of C-op are the same as the objects of C, right? The morphisms of C-op are the same morphisms of C, just considered in the reverse direction. It's the same object, it's the same morphism. They're just considered as going in the opposite direction. They're considered as a morphism in the opposite direction. And so like if we have considered the category set and we consider set op, you folks know the category set, what are the objects of the category set? Sets. Yeah. What are the morphisms of the category set?
Set of morphism.
Well, yeah. I mean, we have a very good name for them. What are the objects of category set?
Functions.
They're functions from one set to another. So if we consider set op, what are its objects? What are the objects? They are what?
Sets.
Sets. That's right. What are the morphisms of set op? They're the same as in set, but they're considered in the opposite direction. They're not functions anymore. They're co-functions. They're not functions necessarily, right? In general, considering a set, if we consider something mapping from, from 1, 2, 3 to the set 1, 2, 3 to the set A comma B, right? Like if we have a function that maps from 1, 2, 3, the set 1, 2, 3 to the set A comma B, if we consider it as mapping from the same map, but going in the opposite direction, from AB to 1, 2, 3. It's when I say the same map, I mean it's okay. So maybe 1 went to B, right? But maybe 2 also went to B, and now we consider the opposite, and maybe 3 went to A, right? We consider the opposite direction. Okay, B has to map to 1 and 2. Okay, that's not a function, right? In a function, you can't have like B got a 1 and 2. It can be it's a co-function. It is a sort of relation from B to A, but it has more structure than that. It's a co-function, and that's a thing. And you can find pages about co-functions, and you can find John Byes talking about co-functions in certain places. Anyway, so when we have a category C, the objects of C op are the objects of C. The morphisms of C op are morphisms of C considered in the opposite direction. We're going opposite. That doesn't mean they're the same sort of thing, like function, co-function versus function. But it's not like it's the inverse of it or something like. It's not like it's one is like I don't know, it's a square and the other is a square root or something like. Anyway, I'll stop saying. Sorry, I shouldn't say it's. Yeah, I mean it may actually sometimes be the inverse, but sometimes it's not a function. Is the point? Just because it's a function one way doesn't mean it's a function in the other way. And when we say the inverse, like square root is the inverse of square, we're often assuming that it's a function. It's a co-function. It's a co-function. Anyway, okay. So let's consider back to basics. So let's consider our product category C up cross D. The objects of C up cross D are an object of C and an object of D, right? So if we consider B comma C, that's the set of arrows. That's a set, and it's the set of morphisms that go from B to C. It's a set of morphisms that go from B to C in the set of these bridges from B to C. And I made the mistake of only drawing one. I could have drawn several here from this to this. But it's the set of them. And you've seen this before. You've seen something like this before, because when you have two objects and you consider the Hom set of those, within a category. Like if I consider the Hom set A comma B. Normally we're not thinking about that applied to morphisms for some reason. We think of it applied to objects, but we get the set of morphisms from A to B, right? Right? Hom sub C, the Hom set for category C of A comma B gives us a set, and it's a set of morphisms, right? From A to B. Here, I'm saying B comma C gives you a set of heteromorphisms, these bridges from B to C. So you've seen something kind of like this before, and in fact, that Hom thing you've been using is a Hom profunctor. It is a profunctor. You just never thought of probably applying it to morphisms. But if you were dealing with representable functors, you would, because that's part of reason about representable functors, which are really tied in with CATLAB and doing the Yoneda cache and doing rewriting and all that sort of stuff is using representable functors, which use the Hom profunctor. And you're lifting operations with it. You're applying the Hom profunctor not just to pairs of objects, but to morphisms. And it's really cool. It's really cool.
Can you explain again why we use COP instead of C? I'm not sure what we get from that.
Okay. So COP, why COP? It has to do with thinking of pre-composition here and post-composition here, but like the COP is not going to affect it listing the set of heteromorphisms from B to C, right? Like when you consider this on objects, you don't have to worry about the op. When you consider on morphisms, that you have to think about the op, right? And this, I may be getting a bit ahead of myself, but I'll give a sneak preview on that, Eric. So this is a functor. It's a functor. Profunctors can be unpacked as a functor. And this functor, if applied to a morphism in D, from, let's say, C to D, and so a functor can be applied on morphisms, and a morphism in this category is a pair of morphisms in COP and D. Okay, so remember, an object in this is an object in C, an object in D. A morphism in this product category is a morphism in COP paired with a morphism in D. So let's consider a morphism in COP. Well, there's a morphism from B to A in COP. There's a morphism in C from A to B, but a morphism in D, in COP from B to A. It's this morphism, but it's considered the other way. So it goes from B to A. Do you agree with that? That there's a morphism from B to A in COP?
Yep.
Okay. In D, let's consider the morphism from C to D. This here morphism. Okay, so those are two morphisms. One in COP, B to A. One in D, C to D. I'm saying I can lift those to get a set of morphisms from A to D. A set of ways of going from A to D. And that will be, you follow this down here. That's why it's reversed, right? See, op, I could follow this. The fact that I considered it as going from B to A, let me start at A, get to B, go from there to C via the set here from B to C, and go to D. So the fact that it's COP, not DOP, meant I could sort of follow it over here down to B. I could start at A and be starting at A, get to B, go to C, and then go downstream of that. If it had been DOP, I'd have to go upstream from this, and it wouldn't make sense.
Well, and that's why I'm confused, because aren't you going upstream on COP or on COP? You're saying you're going from A to B in COP. How is that?
No. A morphism in COP. So we're going to consider a morphism in COP that is going to be one from B to A in COP. That's a morphism in C from A to B, right? A morphism in COP from B to A in COP is a morphism in C from A to B. Do you agree with that?
Yeah.
And so we're going to take a morphism in C op going from B to A, this one here, considered the other way, B to A, and C op, and a morphism here, C to D in D. And that's a morphism in C op cross D. And that is going to go to a set of ways to get from A in C to D in category D, in this target category. So remember, a profunctor it's a profunctor from C to D. And it tells me about ways from getting from an object in C to an object in D. And that's what, in order to do that, we have to take into account the fact that to go from an object in C, we have to go follow an arrow downwards here. And that's why it's C op over, and then follow it here in this direction to the one that we specified. So the fact that we have this means that if we go from A to D, we have the appropriate set of morphisms here. It's objects. So here, reasoning about C op gives us what we want and saying we start from an object in C and we go down from it. And then we go over to D and we go to the target. We can follow things downstream from that, whereas we come from upstream in C. And that's why there's a C op. We'll talk about this more next time. I told you this is a preview, and that's where this will come in, because we're coming from upstream in C. We're going to downstream in D. When we consider starting in C, those are things upstream from the bridge. We're going over the bridge, and we can get to places downstream of that bridge, the terminus of that bridge in D. That's why it has to be C opt here, for it to be a profunctor from C, not C opt, from C to D. And this allows us to turn a way of getting from B to C into a way of getting from A to D. So that's what the profunctor gives. It's this ability to go, if I know ways of going from B to C, I can go from any way upstream of B in C to any place downstream, upstream of B in category C, to a place downstream of this place in D.
Yeah, I got a goal. Got it.
Yeah. Okay. Okay, that's all we have time for today, and I have to get over to, I like the responses here. Awesome. Okay, I have to get over to the faculty club, university club, for lunch. Take care there.